right, we left off with step 1 of phosphate, KB1. And so we're going to go on to step 2. In step 1, it came out 6.7% ionized. And that's the percent ionization in phosphoric acid. So that's why we consider it a weak acid, but it's on the stronger end of the weak spectrum. So this is 6.7% here. Did I do step 2 for this? No? All right. This is KB1. This is going to produce the most hydroxide, which wasn't a tremendous amount. If I was only interested in pH, I'd probably stop here. Let's take a look at KB2 for phosphate. KB2, we're looking at monohydrogen phosphate now. Oops, did I see if I started the recording? Yeah. So monohydrogen phosphate plus water. Monohydrogen phosphate is what we call an amphoteric species. Amphoteric or amphiphilic means that it could either be an acid or a base. But what we have here is whenever we're dealing with a base solution, we just look for hydroxide producers. So even though this can go either way here, it'll be a base in this context because what we're looking at is we're looking at a sodium phosphate solution. Now, if it were alone, we handled this differently. If this were alone, we would treat it as amphoteric. And so let me put a little asterisk here. I'll put it, let me see where I can write it. I'm going to write it over here on the left. If HPO42- was the given, for example, the solution wasn't sodium phosphate. The solution was sodium monohydrogen phosphate. Then we treat it differently. And so let me talk about this. This is called an amphoteric salt. So we have different kinds of salts. When we look at a salt, first we analyze what type of salt we have. So let me do this in black here. We have neutral salts. Neutral salts would be things like sodium chloride, potassium nitrate. Sodium ions are neither acidic nor basic, but chloride is base. But the chloride base is so weak because it's the conjugate base of chloride is the conjugate base of a strong acid. Conjugate base of a strong acid is so weak we consider it neutral. So weak, considered neutral. So when you did the pH measurement for sodium chloride, it was supposed to come out to pH 7. I don't know how close to pH 7 you got, but we have to worry about CO2 contamination of our solutions. But these should be pH 7. Potassium nitrate. Nitrate is the conjugate base of a strong acid, nitric acid. This should be pH 7 too. Even though nitrate's on the base chart there, it's extremely weak. In fact, all those ones, if the acid's very large, the Ka, then that means the base is very small, and so we don't even have a number for those particular ones. And so we have neutral salts like that. Usually group 1, maybe even group 2, actually, and these ions here. All right, the next category of salts that we have are, acidic salts. Acidic salts would be something like FeCl3. The chloride's neutral, but the iron is not. Do you see iron on the chart up here? Can you find iron on the chart? Actually, maybe I should bring up the acid chart here. It's probably easier to see. Let me bring it up. Do you see iron? If we look at iron's position in the chart, here, it's the hexaaqua. So whenever iron's in solution, it can be attacked by water. And so we have hexaaqua. Although the aqua is not, strongly binding. There are different ligand strengths. There are ligands that bind so strongly to the metal that we call them inert. And then there's other ligands that bind kind of weakly to the metal, which we call labile. And so these waters can break off and attach, but it's the hexaaqua. So you put iron 3 in. Iron 3 is high charge. That's a high charge, so the delta minus end, the oxygen, is going to want to attack the iron 3. It's just positive and negative attraction. And so we form this hexaaqua complex. But this hexaaqua complex is a proton donor because when you have a water attached to an iron 3, it changes the electronic environment around the water. And so even though a lot of people think, well, iron 3, that's kind of odd for an acid. Where is my... what we're looking at here is FeCl3 aqueous, which is going to produce Fe H2O 6 3 plus, the complex. And normally water is not all that acidic, but consider this water. Now we have a water bonded to an Fe3 plus, and it's going to form a coordinate covalent bond like this. And when you look at this, this makes this water look very hydronium-like. Hydronium is H3O plus, and if we replace the iron 3 with a H, then we have hydronium. Like I said before, we do not do formal charges. The formal charge on the oxygen here should be positive, but we don't do it. We just leave the water as neutral. But what that does is it makes it very different than a normal water. A normal water doesn't have this going on. A normal water is like this. And so when we look at a normal water, the delta plus on a normal water, when we look at the bond polarity, oxygen is going to be delta minus, hydrogen is going to be delta plus. So the delta plus on this is significant, but when we compare it to the delta plus on this water, it's quite a bit bigger. And so this delta plus is quite a bit bigger. Why? Because of this. So we call it the inductive effect, or there are different things here. I told you not to do formal charges here, and we usually don't represent. We just say the waters are still neutral. So we have 6 neutral water molecules and an iron 3 plus. So that's why I left this, and this is. But in reality, this should be now an iron 2, and this should be a positive formal charge on the oxygen. If we were to do it based on Lewis structures. But anyway, if you have this positive iron 3, it's sucking the electron cloud out. And do you guys remember the inductive effect from Chem 1A? Yeah, it's going to withdraw the electron density, making this one much more polar than this one. And so when we compare the two bond polarities, there's a significant difference in the bond polarities here. Like, for example, the bond polarity here, yes, it's going to be pulled. Oxygen's more electronegative here than hydrogen. Oxygen has a 3.5. Hydrogen is a 2. What is it, hydrogen? 2.1. Over here, this is going to be a heck of a lot more polar. The electron cloud density should be highly polarized, whereas here it's less polar. And what that means is that this is going to be more positive. And so if a base comes along, the base is going to be more attracted to this higher positive charge, like hydroxide. You know, hydroxide's negative, and it wants positive. And so if hydroxide wants positive, which of these two positives looks more attractive to a hydroxide? Well, this one does here. Does that make sense? But we can get a weak base like water. You know, a weak base like water is still, which one's going to be more attractive to a weak base like water? Well, this one on iron is going to be quite a bit more. And water hits this one, then we have autohydrolysis or autoionization of water. And so what that means is that that iron 3 is slightly weaker than what acid? And slightly stronger than what acid? It's stronger than what? Nitric acid? No, that's not nitric acid. Somebody? No? What acid that is? HNO2. Nitric acid is not HNO2. Nitric acid is HNO3. HNO2 is called, if you have one less oxygen than, than the ick, then we call it the nitrous. Do you guys remember per ick, aus, hypoaus? Yeah. So nitrous acid. So it's stronger than nitrous acid, stronger than, what's HF called? Hydrofluoric acid, but weaker than phosphoric acid. Phosphoric acid is one of the stronger weak acids. The strongest weak acid on this chart is this one. This one's called trichloroacetic acid. And then bisulfate. Bisulfate is not a strong acid. Bisulfate's a weak acid. A lot of people treat that as a strong acid. It's wrong. And then phosphoric acid, and then hexaaqua, iron 3, and then nitrous acid, and then hydrofluoric acid. Have you even looked at this chart yet? Can you name all the species on this chart? You should be able to name all the species on this chart. Okay. So one of the things that makes an acid, is having a positively charged. The more positively charged the hydrogen is, the more proton-like it is. Because normally when we think of acid, we think of proton or hydronium. And so the more positive charge we have, in a proton we have a full positive charge, the better, the stronger the acid. So we expect this one to be a stronger acid than water, even though these are water molecules as ligands. Mm-hmm. When we're thinking of acid, we think of H plus or H3O plus. So the more H plus like it is, the stronger the acid. So let me just give you another example here as a test. Should this be even more acidic because it has a lot more hydrogens? So is this what we call a tetraprotic acid? And why not? In fact, most people don't consider methane as an acid. Most people don't consider methane as an acid because, the bases aren't going to be very attracted to methane. Why is that? The bases aren't going to be very attracted to methane because, what we want is, remember, as far as charge potentials go, this is kind of blue. This is going to be dark blue. Dark blue. Here, the hydrogen is going to be dark blue, let's say. I should have picked a different color here. But these hydrogens aren't going to be very blue. These hydrogens are going to be quite what color? Not red. What's the other color? Green. These hydrogens are going to be quite green. The bases aren't really attracted to green hydrogens. They need some positive charge to be attracted to it. Green hydrogens would be close to neutral, right? So this is not acidic. In fact, we don't even consider methane an acid. However, some people want, natural gas. Unfortunately, like in a lot of places, there's natural gas that seeps from the ground. Have you heard of that? But it's not so much natural gas that they're going to go out and capture it. And so they just let it seep out into the atmosphere. In Santa Barbara, there's a whole bunch of places where natural gas is just coming out of the ground and just going into the air. Natural gas is a greenhouse gas. But what would be best is to capture it. And so some people want to capture the natural gas. Natural gas burns quite cleanly, but people want to convert this into gasoline. Well, gasoline, this is a single carbon hydrocarbon. Gasoline are long chain hydrocarbons and other things. And so what they want to do is they want to do this. They'd like to pluck off a hydrogen. If they can pluck off a proton, then they can maybe get other ones to link up together. And if they can get them to link up together, then they could make longer and longer chains. So a lot of people are interested in getting methane and other hydrocarbons to react. Well, one way of getting them to react is, these aren't very acidic, but if you have a super base might be able to pluck a proton off methane. What's a super base? As far as bases go, let's take a look and see if we have any super bases on our chart. We don't. Do you remember the zigzag? Does anybody remember the zigzag method of using these charts? We want to go downhill in terms of energy. So if I want hydrogen, I want to pluck a proton off hydrogen, I need a base stronger than hydride. Hydride's not going to be enough. And so if I go to oxide, oxide's going to be too weak, because if I go hydrogen here, if I go hydrogen here and I try to use oxide, I'm going to make hydroxide. Hydroxide is an even stronger acid than hydrogen. Even though hydroxide is a strong base, but in this context, hydroxide is amphoteric. Hydroxide can either act as an acid or a base. Hydroxide can lose a proton to form oxide, or it can gain a proton to form water. So hydroxide is an amphoteric species. Ammonia is an amphoteric species. Also, ammonia can lose a proton to form amide, or it can gain a proton to form ammonium. HS minus is amphoteric. HS minus can act as an acid, lose a proton to form sulfide, or it can gain a proton to form hydrogen sulfide, H2S. And so anyway, if we go hydrogen here, oxide, we form hydroxide. That's going uphill. This is not thermodynamically favorable. We need to go downhill. So if I want if I want to form hydride from hydrogen, I need a stronger base than hydride. A stronger base than hydride is this one. Do you know what this base is called? If this is hydride, look at the pattern. If this is hydrogen, that's hydride. If this is methane, this is... Do you see the pattern? If this is hydrogen, this is hydride. If this is methane, this is called methide. And so if I wanted to pluck a proton off hydrogen, I'd have to use methide. And so methide comes, plucks a proton off, we're left with hydride, and methide gains a proton to form methane. Methane is a weaker acid. So in order to get methane, I want to pluck a proton off methane to form methide. I need a base stronger than methide. Do you see any bases stronger than methide? Does that mean they don't exist? No, it means that they didn't bother writing any bases strong because this is already getting extreme. These are the extreme ends of chemistry here. And so this is already kind of getting extreme. We need what we call methide's a super base. We need a super base stronger than methide. Actually, there's a chemistry professor at USC, but he passed away, but he is a Professor Ola at USC, and I visited USC because I was thinking maybe I'll go to graduate school there, and so I went there. Ola wasn't available because he's a Nobel Prize winner for his work on super acids and super bases. So he won the Nobel Prize. So I just met with one of his graduate students there, I think. This is a long time ago. But he's doing some very interesting work because he was trying to convert things like methane into gasoline. How do you do that? Well, you got to get it to react. How do you get it to react? Well, you could use super bases. And then he was looking at super acids too. So very famous chemist. Mm-hmm.
Are we going to get this chart on the next exam?
Yes. Well, you usually get this chart on this next exam. I don't know. Maybe, yeah. Yeah, on the next exam, I'll give it to you. For 17. Normally, this chart is available. You know, it's also here in this room, but let me think. Yeah, I'll probably give it in the next exam. But we know, you know, these are the bluest of hydrogens here. These are extremely blue. Do you guys remember the electrostatic potential maps from Chem 1A? Blue means what? Positive or negative charge? Positive charge. These hydrogens are very blue. This bond is very ionic, or, you know, it's not ionic, but it has a lot of ionic character in it. These are all polar covalent bond, borderline ionic bonds. Then as we go down, what typically happens, the hydrogens become more and more, what color? Green. Less attractive to bases. Right? Why? Usually it's because of the different factors, like polarity, usually bond polarity. That's one factor influencing. There are other factors though too, and some of the other factors are kind of weird because let's rank these acids here in terms of blue and green. This is unusual because which one's a stronger acid, HI or HCl? HI is a stronger acid. HI is the second strongest acid on this chart, hydroiodic acid. But which one is more blue? In other words, which one has more positive charge on the hydrogen, HI or HCl? Which one is a more blue hydrogen, HI or HCl? HCl is more blue. Why is that, Giselle?
It's more electronegative since we have more.
Yeah, exactly. Chlorine's more electronegative. And so this is kind of weird because this is more blue than that. That's a lighter blue. This is a darker blue. Right? But why is HI a stronger acid? HCl should be a stronger acid. HCl should be a stronger acid because it's more blue. And if you're a base like hydroxide, hydroxide's negative. Negative's seeking out. Hydroxide's red, right? And so hydroxide, this red is seeking out blue. And this is more blue. And so you know what? Hydroxide attacks this more. Hydroxide for sure is going to be more attracted to HCl. But there's one problem with HCl versus HI. You know, It's not really a problem. There's one thing. What else do we want to know about this? Well, the chlorine is what we call a third period. And then iodine is, let's see, first, second, third, fourth, fifth period. And when we think about that, what comes to mind? What are some of the differences between chlorine and iodine? The size. Chlorine is small. Iodine is huge. Iodine's huge. And what type of bond is this? Well, it's a polar covalent bond, and what we're going to say is that iodine is sp3 and chlorine. Hybridization is more important when we're dealing with small atoms. Less important than when we're dealing with big atoms. And so the amount of hybridization varies depending on how big and how small, because hybridization is going to be a result of minimizing the repulsions, VSEPR, valence shell electron pair repulsions. So anyway, iodine's probably not sp3. Iodine's probably unhybridized. So this is probably an sp sigma bond, and this is probably an sp3 sigma bond. Do you guys review the bonding chapter 11? Good. So anyway, what we have here is this. The bond is going to be very different between HI and HCl. Let's take a look at that. So one of the things we look for is blue, how blue it is. But the other thing we look for is this, acid strength. We have an IH and an sp3. Then we get decent overlap here. This is valence bond theory. We use valence bond theory often, even though MO theory would be better. It's just easier. Versus if we have H and an I, and we look at it, I'm not color coding this. This is not green as in neutral. This bond is polar. The iodine HI bond isn't so polar, but the HCl bond should be quite polar. It should be quite polar, which means the hydrogen is going to be a lot more bluer. Here, this hydrogen. Actually, I should probably do that compared to this hydrogen, which is a lot less blue. This is a hydrogen is much more green. Yeah. So for sure, all the bases are going to be attracted to the hydrogen on HCl. And so if you're a base, which is red, you're going to be after the blue here. And this one, and so this one's going to be attacked much more. But even though this one is attacked much more, this one is a lot, what? This one, there's going to be a tug of war here. So the base comes in, and it's going to try to pull the proton away from chloride. So tug of war. And then a base comes in here, and it's going to be less attractive, but it's going to pull the proton away from iodine. Which one is it going to be more successful in taking? The proton from chloride, or the proton from iodide? Iodide. Why? Because it's a much weaker bond. And so this is a weak bond. So even though it isn't as attracted to HI, it's just much easier to break that bond. And therefore HI is what we call a stronger acid. Did you hear this stuff before in Chem 1A? So this is kind of weird because, most of the pattern in this acid chart is it gets more and more blue, and we get stronger and stronger acid, and it gets more and more green, we get a weaker and weaker acid. But there are some contradictions here, and that is especially with this. So this is in chapter 17. It's the HI, HBr, and HCl. HI is the strongest, even though the bases aren't attracted to it, because it's a lot easier to take the proton. And then HCl is weaker, even though bases are more strongly attracted to this, it just can't pluck the proton off as easily. And so this is inverted than what you'd expect. So what this tells us is that the most important factor that we usually look at in acid strength is how blue it is or how strong the bond is. What is more important, how blue the proton is or how strong the bond is? Bond strength. Bond strength is overriding. So the first thing, whenever we look at for acid strength, we first look at how strong is the bond. If the bond is weak, then it's going to be a stronger acid. And so we look for that. You know what? Which one of these, HI, HBr, HCl, which one is missing out of that list? HF. Out of these, HF, HCl, HBr, HI, which one of these is going to have the bluest of blue protons? HF. So the bases are going to be most strongly attracted to this, hydrofluoric acid. But why is it down here? And in fact, it turns out if we compare HCl and HF, if we look at the Kas, and we can look at the Kas for HCl, there is a Ka value, but we just don't usually do the calculation because it's so big that really leaves practically no reactant left. And if you had a liter of solution, there's less than one. And so, anyway, HCl compared to HF, HF is 1,000,000 times weaker. If HS is 1,000,000 times weaker, does that mean it has 1,000,000 times stronger bond? So, I told you, well, what's the strongest bond that you can think of? Covalent bond. Or what do covalent bonds range from? What to what? 100 to 1,000. 100 being on the weak end for like peroxide-like bonds, 160 or whatever it was, or iodine, And so 100 to 1,000. At the 1,000 was what bond? Nitrogen triple bond. So we're looking at single bonds here. And so that means single bonds around 400, 300, 400 kilojoules per mole, right? And so what that means is, okay, if this is about 300 kilojoules per mole, then if this is 1,000,000 times stronger because it's 1,000,000 times weaker, then this must be 300 million kilojoules per mole. Does that make sense? A bond in 300 million kilojoules per mole, would that make sense? That would be how many times stronger than nitrogen? That'd be 100,000 times stronger than nitrogen. Is that possible? No. And so the point of this is this. Why is HF 1,000,000 times weaker? Because it cannot have 1,000,000 times stronger bond because bond energies range from 100 to 1,000. And so where are we getting millions, hundreds of millions of kilojoules per mole? We aren't. And so the reason why HF is so weak, HF is unusually weak. It's 1,000,000 times weaker than the others. So we have HI, HBr, HCl. They're all around the same. HI is a little stronger than HBr, which is a little stronger than HCl. But then HF is the odd one out. HF is way down here. And so we look at different things. So here we're looking at what we call polarity. Polarity is the number 2 thing we look at in bond strength. Oh, not bond strength, acid strength. Sorry. In acid strength, the number 2 thing we look at is polarity. how blue it is. The more blue, the better. But the number one thing we look at is bond strength. And so this explains the reason why the strongest acid is HI. HI is stronger than HBr, and HBr is stronger than HCl. And HCl is much more stronger than HF. But the number three thing we look at is the stability of the conjugate base. Stability of the conjugate base. The number four thing we look at is what I'm going to call is hydration. This is the stability of the hydrated products. So in terms of stability, what's more reactive, like high voltage or low voltage? What do you think is more reactive? High voltage or low voltage? High voltage. And so a voltage is just the concentration of charge. So let's look at iodide versus bromide versus chloride versus fluoride. All these are -1. But in terms of stability, which one is going to be the most stable, least reactive of these? Yeah, which one's the most stable, least reactive? The fluorine? Why is the fluorine? Let me ask you, electronegativity. What's fluorine's electronegativity? Anybody remember? 4.0. What's the electronegativity of fluoride? Is electronegativity of fluoride still 4.0? No, the electronegativity of fluoride is way, way below 4.0. I don't, when I think of fluoride, fluoride doesn't even want an electron, does it? Because if fluorine gains another electron, it forms fluoride with a 2- charge. Have you ever seen fluoride with a 2- charge? Why not? Or maybe it gains 2 more electrons, fluoride with a 3- or fluoride with a 4-. Why doesn't it just keep gaining more and more electrons? Why does it stop at 1? If fluorine's the most electronegative, shouldn't it also be the most greedy? But it stops at 1. It doesn't gain 2, doesn't gain 3, doesn't gain 4. Why is that? It stops at 1 because it fills the shell. And if we gain more than 1, it's going to go into the next higher energy shell, which is totally unfavorable energetically. This is going to cost too much energy. It might want another electron, but it has no place to put it that's reasonable. But anyway, so when I think of anions like this, I don't think in terms of electronegativity, at least the Pauling's electronegativity. And so I don't really consider fluoride being very electronegative at all. And the same thing with, if I had fluorine with a plus, let's say I knocked an electron off fluorine, what's going to happen to the electronegativity of fluorine? Is it going to stay at 4? No, this is going to be way bigger than 4. And so electronegatives change depending on the charge on the species. And so in this case, I wouldn't want to use electronegativity for this. I want to use like voltage, you know. Or other things. I mean, other things would be like this. You know, if you had, let's say, a 10-pound weight on your foot, right? If the 10-pound weight on your foot was on a pin point like this is 10 pounds, versus if you had a 10-pound pad like this that's cushioned, this is 10 pounds. Would you say, it's the same, it's 10 pounds is 10 pounds is 10 pounds? No, you'd say my foot is going to feel a lot more pain if I had a little pointy 10-pound object resting on my foot versus a cushioned 10-pound object, right? So which of these 4 is more reactive? In other words, also with voltage, you know, you have that static electricity. If you take all that electricity, like you walked across the carpet with your socks or something like that, and you touched a metal doorknob, and then you have a little bolt of lightning touch your finger, like this. Versus if you take all that static electricity and spread it all around the room, then it's different. You know, it's like water, you know. So, or maybe visually it helps. Which one is the most blue out of all of these? Or are these blue or are these red? These are blue. Which one is the most blue out of all of these? Red is, you know, oh yeah. Which one is most red out of all these? Red is for what? Positive? Blue is for? Blue is for positive. Okay. See, I still get it mixed up. I still get it mixed up because whenever I think red and black. Red is for positive and batteries. Be very careful. You know, red is the positive terminal. And so, which one's the most red out of all these? Or are these all the same? Fluorine's the most red, or fluoride's the most red. And the least red would be iodide. And we call this charge density. Iodide has the lowest charge density, so it's going to be the least reactive. Fluoride has the highest charge density. It's going to be the most reactive. It's going to have the highest voltage, highest potential. You know, if we're talking about electricity, if we spread it out versus concentrated, it's going to react differently. So, out of all these, which one should be the most stable? Iodide. Iodide should be what we say is lowest charge density, most stable, weakest conjugate base, weakest CB, conjugate base. And this is going to be the least stable, the strongest conjugate base. So that also predicts HI to be stronger. So we have two things for, one thing against. And this is where we have to use a combination. We don't know, is polarity more important or is bond energy more important? And so what we do is we combine this with experimental data. Experimental data tells us HI is stronger. Therefore, based on our experimental data, then we predict that the bond energy is most important. And versus polarity. Polarity gives us something that doesn't agree. If we look at bond polarity, we'd expect HF to be the strongest acid. Theory should be able to also reproduce these results, but this is just based on observational studies now. And then this one, the stability of the conjugate base, iodide's more stable because it's less concentrated, right? More stable. And so normally when I think of these, I don't think in terms of electronegativity. When I think about bond polarity, I think of electronegativity here. However, it still doesn't quite explain HF. Fluoride is not a million times less stable than the others. You know, it's just a little smaller than chloride. It's not a million times smaller, is it? No. It's not a million times smaller. So that brings us to number 5, or number 4, sorry. Number 4 is going to explain why. Hydration, in other words, the stability of the hydrated products. So what happens is, for some of these, like iron, the interactions are quite strong, and we form ligands here. But in this case, we form hydrated ions. And so the hydrogen ends of the water molecules are going to help stabilize the negative charge on the ion, because the hydrogen ends on the water molecules are delta plus. And so we form what are called hydration spheres, like this. And so there could be 4 kind of like this, and then 1 above and 1 below. So typically we can fit like 6 water molecules around there. And these are very labile. I mean, these are exchanged continuously. And so, you know what kind of intermolecular force is holding these two? Even though iodide is not a molecule, we just call it an IMF. The force of attraction here is called an ion dipole attraction. Ion dipole attractions, you call, can be quite strong, stronger than hydrogen bonds, even. And so hydrogen bonds are like 25 kilojoules per mole, so these can be quite significant, in fact, the hydration spheres. And so in the dissolution chapter, in the dissolution section of chapter 14, they talk about this. You know, when you dissolve things, you got to break the solute-solute, you got to break the solvent-solvent, and you got to form the solute-solvent. This is a solute-solvent interaction, and this can be quite strong, the ion dipole attractions here. So which one is going to have stronger ion dipole attractions? In other words, which one is going to form more stable hydrated ions? Which of these is going to have stronger ion dipole attractions? This should be more orderly than I drew it. In other words, which one's going to give a stronger positive negative attraction? The hydrated iodide or the hydrated fluoride? Which one's more stable? Iodide because of what? So you got to start trying to visualize it in terms of this. The positive end of the water molecules is blue or red? Blue. And the ion is going to be red. And which one of these is going to be more red? The iodide or the fluoride? Fluoride. So if the blue is seeking red, which one's going to be more attractive? The fluoride, and therefore the fluoride's more stable. I might as well I want to do another aside here because there's another thing that is explained by number 4 here. This is in redox chemistry, and so this is another side topic here. Which metal atom is easier to ionize? Lithium or potassium? Which one has a lower ionization energy? Which one has a higher ionization energy? Yeah, lithium has a higher ionization energy. If lithium has a higher ionization energy, that means, is it easier to take an electron off or harder to take an electron off? It's harder to take an electron off lithium than it is potassium. So on the same chart here, let me save this before this crashes. On the right side, we have the acids. On the left side, we have the redox chart. Which one is a stronger reducing agent, lithium or potassium? You know what the strongest reducing agent on this chart is? Lithium. And what do reducers do? Reducers lose an electron to form lithium ion. And so reducers give up electrons. Well, there's a problem here. This is a problem you would notice if you do the daily. If you do the daily, you start to notice things that don't quite make sense. When you review it, and then you continue to review it, and then you try to figure out what's going on here. One of the things that's weird is potassium is bigger, lithium's smaller. This is wrong. Potassium should be easier to ionize. Therefore, this is ionization of potassium. It should be easier to ionize than lithium. Why the heck is lithium stronger, meaning it's easier to ionize lithium than potassium? When we look at the ionization energies, the ionization energy of lithium is greater than potassium. It doesn't make sense. Not only that, when you react lithium, lithium is so easy to ionize, water ionizes it. Water is not a very good oxidizer. So what we can do is we can oxidize both lithium and potassium with water. And so if you throw lithium in water, it's a little bit violent, but if you throw potassium in water, it's like explosive violent. Potassium is much more violent than lithium, so that says, well, potassium should be at the top. The right side, the top is here at the bottom. The left side, the top is at the top. And so potassium should be at the top of the reducers, right? Reacts much more violently. It has a lower ionization energy. Why the heck is it not at the top? It doesn't make sense. So these are I told you maybe I told you this. I told the Chem 1A students this. That most of the exams I took at UCLA, it was 90% recall. If you recalled everything from the lecture and the class, you could get an A. And I always thought that the extra 10% was challenge problems. And so this would be a challenge problem. A challenge problem would be okay, this doesn't make sense. Describe what's going on here. That would be a challenge problem. Because they would have never talked about it. You would have had to know that, or you would have come up with some kind of hypothesis why that is. And so do you have some kind of hypothesis why that is? This is our observation. This is experimental fact. Experimental facts are fine. Theories, if the theory can't describe the underlying experimental fact, then there's something wrong with the theory. And Before we even get to theory, we want a hypothesis. So what's the hypothesis for this?
What's the question you're asking?
The question is, why isn't potassium at the top? Potassium is bigger than lithium. Potassium is easier to ionize than lithium. Potassium visually reacts violently with water, whereas lithium reacts much less violently with water. Once we were at UC, I remember this vividly. Once we were at UCSB, and some other lab, they wanted to get rid of potassium, so they had a 1 pound stick of potassium. It's like this big, and they wanted to get rid of it safely. So they took it to there's a faculty pool there, and there's usually nobody there, and they decided they're going to dispose of it in the faculty pool, and then this is going to adjust the pH a little bit. A little bit higher. So they ended up throwing it into the faculty pool, and it resulted in this big explosion. And I remember this plume of water going up like 30 feet in the air, and just a bright flash. It was very, very impressive. I've always taken little chunks of potassium, but never a 1 pound stick. It was really loud too. And so fortunately nobody was around, and it was surrounded by a big fence. So they didn't. Those were crazy days, and eventually those days have long gone, where we did such crazy stuff. Because one day the FBI showed up at the department and ended up arresting some people in the chemistry department there. But it turned out they were released a little bit later. But so it's weird. They didn't take a 1 pound. If they took out a 1 pound block of lithium and threw it in the pool, it'd be dud. It'd be kind of boring, wouldn't have been very exciting. So anyway, what's going on with that? What's going on with that is we have to look at the stability of the product. When we look at the stability of the product, it makes sense. So potassium ions are more stable. They're bigger than lithium ions. Lithium ions are more smaller, so lithium ions should be more reactive. And so when we look at that, but then we have to look at the stability of the hydrated product, right? Because these are aqueous ions. And then when we look at the stability of the hydrated product, it turns out that lithium ions, being a lot smaller, form much more stable hydrated ions than potassium ions. Potassium ions are kind of big, and so therefore the hydrated potassium ions aren't so stable. And so overall, thermodynamically, this goes to more stable product. And so this is why lithium's at the top, because eventually it's going to result in more stability. However, it's a bit slower. Whereas potassium doesn't result in as stable of products. And so, and potassium is much more exciting than lithium. Although lithium can be very exciting too, because you have the lithium fires with the lithium ion batteries and stuff. They're using other things, lithium metal in some of those. And so it could be very reactive as well. Not to say lithium. Lithium is very dangerous. All metals are very dangerous. Metal fires are very dangerous. Do not use CO2 on metal fires. You have to use some other suppressant, because CO2 is an oxidizer. CO2 is maybe a better oxidizer. I don't know if CO2 is better or worse than water. I suspect CO2 is much better oxidizer than water. So you wouldn't want to use CO2, because if you're already having a fire with water, then, or an explosion with water, then you're definitely not going to spray water on this fire. Would you spray water on this fire? No. Uh-huh.
Wait, sorry, you said thermodynamically what?
It's thermodynamically stable.
Lithium?
Lithium ions, hydrated lithium ions, are more thermodynamically stable. So this is from redox chemistry, and it's kind of weird because it's not what you expect. Those are what I call surprises on tests. You want to minimize the number of surprises you get on tests. Like surprise, I have no idea. You want some kind of idea of what's going on. And how do you avoid those surprises on tests? You avoid those surprises by trying to, when you at least start out, trying to see as many, different problems and applications as possible. So, what I'm going to do is I'm going to continue with this because this is the last part of chapter 17, and then we'll go back to the step. The stepwise is just following the same methodology with phosphate. You go to KB2, KB3, and then KW. But I'll talk a little bit more about this here. And so let's take a look at some examples. When we look at base strength, what makes a good base? Let me see. There's other factors here. For Bronsted, it's a bit easier than for Lewis. Lewis, we really should consider MO and LCAO and HSAB. These ring a bell? Like MO is what? Molecular orbital, which deals with LCAO. LCAO is what? MO theory is based on the formation of bonding and anti-bonding orbitals that are a result of molecular orbitals that are a result of linear combination of atomic orbitals. Linear combination of atomic orbitals makes two molecular orbitals. We get an MO star and an MO. So we take two AOs. AOs are atomic orbitals, and we form two MOs. HSAB tells us what forms good LCAOs. What forms good LCAOs we dictate from HSAB. HSAB is called what? So like I said, 90% of the test is recall. How good is your recall? You know, if your recall is very fast, the tests are also timed. You have very little time. Every test I took, there's tremendous time pressure. It was like a sprint. You're always sprinting. And I didn't particularly like that because I liked a more relaxed pace. I didn't like to be rushed so much. But if you have fast recall and you can burn through the recall questions quickly, then you have more time for the challenge problems. But you should never start on the challenge problems, because if you burn up all your time on the challenge problems, then you don't have any time for the recall problems, and you just blew it points-wise. Because you may not, and a lot of the challenge problems people didn't finish. But HSAB stands for hard, soft, acid, base. And so predicting the strength of Lewis bases is more complex. Whereas Bronsted is a little easier. For Bronsted, we're just going to look very simply at what makes a good Bronsted base. At the simplest level, what makes a good Bronsted base is being, I'm sorry? Ability to accept a proton. Right? And so what makes a good ability to accept a proton? Negative charge. And what color is negative charge? Red. And so the more red, the better. And so for Bronsted, we want more red, the better. For strength. So the red can be localized or delocalized. And so the more red, the better for strength. In other words, the more red it is, the stronger the base. However, sometimes we want stability, you know. And if we want stability, then that means the less red it is, the weaker the base, and the higher the stability. The stronger the base, the more reactive it is, and the lower the stability, the higher the reactivity. So this is lower stability. So for Bronsted, it's much easier because all we're going to do is we're going to just look at the charge. When the red is concentrated, we call that localized. When the red is spread out or weaker, we call it delocalized or just a lower charge. And so decreasing the red could be lower charge and or delocalization of charge. That is spreading it out. So when we look at chloride, bromide, iodide, all those have the same charge. It's just how spread out is the charge. That's what we call delocalized or charge density. For increased red, that's going to be either higher charge and or more localized charge. Fluoride versus chloride, which one's a stronger base? Fluoride's stronger. The same charge, the charge is more concentrated, more localized, in a smaller volume of space. Methoxide versus formate. Formate is from formic acid. And so we draw out the Lewis structures for these. Both of these have a negative formal charge. On oxygen, which one's a stronger base? Methoxide is a stronger base. And how did you come up with that? So.
Because it's more localized than negative formal charge.
It is more localized, but why is formate more delocalized?
The double bond.
There are two types of delocalization. That,
Oh, in the resonance.
yeah, this is resonance delocalization. That's good. This is resonance, and the hybrid structure for this is going to have a negative 1/2 charge on each oxygen. So this methoxide is actually a strong base. It's not one of the strong bases that you need to memorize, but it's very hydroxide-like. Whereas formate's like acetate, it's weak. It's weak. This is a weak base. This is called resonance delocalization. And so we have two types of things that we look at: resonance delocalization and the inductive effect. Inductive effect, we look at two things. We look at electron withdrawers. Electron withdrawers are usually electronegative type species versus electron pushers. Let me give you an example of this. Like, which one would you expect to be a stronger base? Hydroxide? Or methoxide? Can I resonance delocalize either of these? Is resonance delocalization? No, it's not possible. So how about the inductive effect? Carbon and hydrogen have about the same electronegativity. And so the electronegativity of hydrogen is a 2.1, and the electronegativity of carbon is a 2.5, 2.4. 2.5? I don't remember. I don't remember because they're two. I mean, some books have it at 2.4, some books have it at 2.5. I haven't looked at Petrucci in a while. It's 2.4, 2.5. I'll go with 2.5 because delta En for hydrogen and carbon is only 0.4. If you have a delta En of 0.4, it makes the bond a nonpolar covalent bond. The cutoff is 0.4 roughly. So based on electronegativity, you would think that carbon is slightly more electronegative. If carbon's slightly more electronegative, then it's going to withdraw some of the electron cloud towards it, decreasing the amount of negative charge here. That's called inductive effect, right? However, is carbon really a 2.5 in this particular compound? And so when we do it, Pauling's electronegativities are just too, what we say, too oversimplified. You know, if you oversimplify things, then sometimes you don't catch the details of this. And so what I'd like to do is when we have substituent groups like this, I'd like to look at methyl. Is methyl a electron withdrawer or is methyl an electron pusher? So this is called the methyl substituent. And so if I have a methyl group versus a hydrogen group attached to my oxygen here, is the methyl an electron pusher or electron withdrawer, or neither? A pusher nor a withdrawer. What would you say? In other words, is methyl electron rich or electron poor? You've heard of electron rich and electron poor before. How do we determine if something's rich or poor? What do we calculate? Oxidation state. So what is the oxidation state on carbon here? When I look at the oxidation state on this carbon, the oxidation state is equal to Can somebody calculate the oxidation state for this?
Oxidation state is winner takes all, right?
Winner takes all.
Two negative?
Okay, yeah, so let's take a look. 2, 4, 6, and loses these. And so, yeah, -2, good. Is that on the rich end of the spectrum or the poor end of the spectrum? This is on the rich end. So this is an electron pusher. Electron pusher means that it's kind of rich, so it's pushing negative charge density towards the oxygen, which means that I predict this one to be more basic. And so I would predict that methoxide should be more basic than hydroxide. This has got an electron pusher group. All right, let's compare to something like this. Is the fluorine substituent an electron pusher or electron withdrawer? This is an electron withdrawer. And that means it should be less basic than hydroxide. All right, so resonance delocalization is more significant, but we have to look at inductive effect, with electron withdrawing and electron pushing. What time do we go to? 55? 11? Okay, so I still have time. Now, resonance can take on interesting forms. So, for example, alcohols aren't very acidic. So when I look at methanol, methanol is a poor acid. Methanol is a poor acid, even though you think it'd be like water, here, because carbon and hydrogen are kind of the same. Carbon is roughly the same as hydrogen in terms of electronegativity, so that really doesn't change the delta minus on here, on the oxygen here. So I think like methanol and water should be the same, but methanol is actually, I think, worse than water. And so if methanol is worse than water, why is that? Well, it could be, well, one of the reasons why is if you're going to pick a hydrogen, you'd pick this one. This would be the bluest of the blue hydrogens here. These hydrogens are green here. This hydrogen is quite blue. This is polar bond, but not super blue. And so if a base comes along and plucks it, we're going to take the base. Our base is going to be water in this case. Really not a very good base, but that's the base that we use for everything. Because that's Ka and Kb rely on water as the acid or the base. So if that plucks it off, one of the reasons why methoxide is such a weak acid is because it forms a terribly unstable product. In hydronium. And so strong base. And so in general, alcohols aren't very good acids because they end up forming really strong bases. Whereas carboxylic acids are good. Carboxylic acids are good because you can have resonance delocalization, you know. Carboxylic acid is no problem. That's going to form a much more stable base. However, there's one acid that's kind of weird. And this one acid that's kind of weird is phenol. It's kind of weird because it's an alcohol. And alcohols we don't really consider very good very good acids. Phenol is unusually acidic. Unusually acidic because alcohols form conjugate bases that are terribly unstable. And so it looks like this one does the same. And then carbon, usually hydrocarbons are electron pushers. Hydrocarbons are electron rich, they're fuels. They like to be attacked by oxidizers. And so typically hydrocarbons are electron pushers, and then we got this. But why is this one? Is it because of the bond polarity? No. The bond polarity is, this is about as blue as the others, And so what it has to do with is the stability of the conjugate base. But my word, Excel has crashed, so I'll be done right now. Unfortunately, I'm not done with Chapter 17, but I'm almost done. So we're still going to have the test next week on Wednesday. I'm going to talk a little bit of it, Chapter 17, on Monday. But I think I had phenol on the quiz. Phenol, the reason why phenol is unusually acidic is because of resonance delocalization of its conjugate base. You can look at this. If you want to look at the structures for resonance delocalization of phenol, it's in the book. You can see how they can delocalize the charge on phenoxide.